Welcome to the today video lecture series on topic reentry aerodynamic heating. So first we have to discuss about what is multi-layer insulation. So thermal analysis of multi-layer insulation for vehicle focuses on protecting the spacecraft from the intense aerodynamic heating experienced during reentry. Reentry generates high temperatures due to the compression of air in front of the vehicle and the frictional heating caused by high-speed flow. And multi-layer insulation is commonly used in spacecraft because it offers thermal protection by using multiple reflective and low conductivity layers to minimize heat transfer. Thermal environment. The thermal loads on re-entry vehicles are extreme, especially in the hypersonic speed. It is important to model the re-entry profile, such as velocity, altitude, and attitude, to understand the heating rates. Aerodynamic heating rate can be modeled using empirical formulas or CFD analysis. Aerodynamic heating rate depends on vehicle shape, re-entry angle, and speed. Materials and layer properties. Multi-layer insulation typically consists of multiple layers of thin metal foils such as aluminized bilayer, a polyester or polythene terephthalene film that can be applied to the facing of foams. This layer of polyester gives a piece of foam added protection against heat and other environmental hazards. Kaptan, a polymerized film used in flexible printed circuits and space blankets which are used on aircraft satellites and various space instruments. The above mentioned materials are separated by low density spacer material. Each layer acts as a barrier, reflecting radiative heat and slowing conduction. Key properties include the emissivity, absorptivity, thermal conductivity of the reflective files, and the separation distance provided by spacers. Heat transfer through multi-layer insulation can be approximated by a one-dimensional heat transfer equation accounting for both conduction and radiation. Due to the multi-layered structure, numerical methods like finite element analysis can be provide accurate predictions. For conduction, Fourier's law can be applied across each layer where heat transfer is hindered by spacers. Radiation exchange between layers can be calculated using the Stephan-Boltzmann law and layer emissivity. And transient thermal analysis. During re-entry, a transient thermal analysis is critical as the heating rate varies over time. The analysis should assess the temperature rise across each layer, and it determines that if the insulation can maintain the inner spacecraft temperature within safe limits for sensitive components. And the figure shows the exact results of the thermal analysis of Orion spacecraft. And these images are represented of the heat transfer through multi-layer insulation. And this equation is P is equal to constant sigma AT power 4. So this is the sigma is a Stephan-Boltzmann constant is the value of 5.67 in 10 power minus 8 watt meters power minus 2 and Kelvin power minus 4. And the temperature also is indicated in Kelvin. So the heat transfer is a MLE is a power radiated in watts, and emissivity it's a there is in no units, and surface area will be located as in a meter square. So this is aerodynamic heating area of this image is corrosion and based used this method. So this is the Kevlar layers and aluminum layer are used in the figures also. So this is a multi-layer thermal heat transfer insulation, and it will be applied in all type of information and communication systems, and especially these type of multi-layer insulations commonly used in aircraft and spacecraft engines. Particularly the aerodynamic gas constant will represent about what about the heat phenomenon area will be increased by various to the other sources of the heat transfer area. The next video we will discuss about the simulation softwares and how it will be adapted in radiation heat transfer. Thank you.